In this lecture, we'll look at how to use right triangle trigonometry to solve right triangles. When we solve right triangles, we'll be given one of two cases. We're either given a right triangle with one side and one angle. Here's an example where we're given one side and one angle of a right triangle. And by angle, we mean one of the acute angles in addition to the right angle. Or we'll be given a right triangle with two sides. Here's an example with two sides given in addition to the right angle. We're going to use our right triangle trigonometry to solve for all the remaining sides and angles. First, I want to remind you of the convention we use when we sketch these right triangles. We use the capital letters, like capital A, B, and C, to represent the angles of the triangle. Angle C is usually the 90-degree angle, but that should be specified in the directions. Then we use the lowercase letters to represent the side opposite the angle with the same letter. So side A is opposite angle A, side B is opposite angle B, and side C is opposite angle C. I also want to remind you of the right triangle definitions for our trigonometric functions. We only need the three primary functions to solve right triangles, because any two sides of the triangle can be found in one of these three ratios. That means if we know one of the acute angles in the triangle and one of the sides of the triangle, we can solve for either of the other sides using one of these three ratios. And if we know any two sides of the triangle, we can use one of these ratios to solve for the angle using the inverse function. Let's see how this works in our two examples. In this first example, we're given right triangle ABC with C equal to 90 degrees, and we're told that side B is 7 inches and angle A is 58 degrees. So first, let's sketch this triangle. Here we have our right triangle with angle C equal to 90 degrees. We're told that angle A is 58 degrees, and we're told that side B is 7 inches. We're asked to solve for the remaining sides and angles, and we can solve for these in any order. Let's go ahead and start with the angle because that'll be the easiest. The two acute angles in a right triangle are always complementary. They add up to 90 degrees, so that the total sum of the angles is 180 degrees. That means that angle B will be the difference between 58 degrees and 90 degrees, which is 32 degrees. Now for each of the two remaining sides, we need to find a trigonometric function that relates the side we're solving for with the given side. Here's a reminder of the right triangle definitions. Let's start with side A. Here we're solving for the unknown side, which is opposite to this angle, using the given side, which is adjacent to this angle. That means we're going to be working with the tangent function, which gives the ratio of the opposite leg to the adjacent leg. So in this diagram, the ratio of side A to side B is given by the tangent of 58 degrees. Notice in this statement, we're just writing out the definition tangent equals opposite over adjacent, filling in the angles and the sides in this diagram. There should only be one unknown in this statement, and we can solve for that, in this case, by multiplying both sides by 7 to cancel the denominator. And that leaves us with A equals 7 times tangent of 58 degrees. Now we can plug this entire expression into our calculator to get A, but it might be helpful to see what the tangent of 58 degrees is equal to. We can get that from a calculator or from a trigonometric table. Here we can see that for the angle 58 degrees, we get a tangent ratio of 1.6003. So A is approximately 1.6003 times 7, and that's approximately 11.2 rounded to the nearest tenth, and our units are inches. Remember that this ratio tells us for any right triangle with a 58-degree angle, the opposite leg to that angle will always be approximately 1.6 times the adjacent leg, or the ratio of the opposite leg to the adjacent leg will be approximately 1.6. Now we'll do the same thing to solve for side C. In this case, we're working with the unknown side, which is the hypotenuse, using the given side, which is adjacent to the given angle. So we need the cosine function, which tells us that the ratio of the adjacent leg 7 to the hypotenuse C is given by cosine of 58 degrees. Here we have our statement, cosine is adjacent over hypotenuse. The unknown value is now in the denominator. We still want to cancel denominators, so we'll multiply both sides by C, and that leaves us with C times cosine of 58 degrees is equal to 7, and we'll isolate the variable by dividing both sides by cosine of 58 degrees. We can plug this whole expression into our calculator, and that gives us approximately 13.2 inches rounded to the nearest tenth. Notice in this table that the cosine of 58 degrees is approximately 0.5299, or approximately 0.53. That means for a 58-degree angle, the ratio of the adjacent leg to the hypotenuse is approximately 0.53, or the adjacent leg is just a little over half the length of the hypotenuse. So when the adjacent leg is 7, we get that the hypotenuse is approximately 13.2. Now let's look at an example where we're given two sides of a right triangle. In this example, we're given right triangle ABC, again with angle C equal to 90 degrees, and we're given side A is 7 meters and side C is 9 meters. Let's sketch this diagram and fill in the two given sides. We're substituting 7 meters for A and 9 meters for C. Whenever we know two sides of a right triangle, we can always use the Pythagorean theorem to solve for the third side. So let's start by solving for side B. The Pythagorean theorem is a squared plus b squared equals c squared, and we'll substitute a equals 7 and c equals 9. Solving for b squared, we get 9 squared minus 7 squared, which is 32. So b must be the square root of 32. And if we were giving an exact answer, we would simplify this radical. Since we're asked to round this to the nearest tenth, we'll plug this into our calculator and round this to 5.7, and our units are meters. Now we need to solve for the two angles. It won't matter which one we choose to start with, because with the two given sides, we can set up an appropriate trigonometric ratio for either one of these angles. Let's go ahead and start with angle A. With respect to angle A, the two given sides are the opposite leg and the hypotenuse. Notice if we were solving for angle B, we would be working with an adjacent leg and a hypotenuse. So for angle A, we want the ratio sine equals opposite over hypotenuse. That's sine of angle A is equal to 7 over 9. Now we can't use algebra to solve for this unknown value. Sine is not something we can cancel by multiplication or division. It's a function. So we need to use an inverse function to get from the output back to the input. In other words, we need to find the angle that has a sine ratio of 7 over 9. Let's see how this looks with the trigonometric table. Here's part of our trigonometric table. Remember, the angle is in the first column, and the sine, cosine, and tangent ratios are in the last three columns. In the previous example, we looked up the angle 58 degrees and looked at its cosine and tangent ratios. Now we want to look up a sine ratio from this column and try to find the corresponding angle. In our example, we have that sine of angle A is 7 over 9. To look this ratio up in the table, we need to write it as a decimal. 7 divided by 9 is approximately 0.7778. Looking that value up in the sine column, we see that it falls between the second and the third entries. So the angle must be between 51 and 52 degrees. We'll use a calculator to get a more precise answer. We use the inverse sine function, which takes the ratio as the input and returns the angle as the output. So the inverse sine of 7 over 9 is approximately 51.1 degrees, and that matches what we found in our table. Let's go back to our example. Here's where we left off. Sine of A is 7 over 9. That means that the angle A is the inverse sine of 7 over 9, which we plugged into our calculator to get A is approximately 51.1 degrees. The last thing we need to solve for is angle B. We could use trigonometry like we did for angle A with the two given sides, or we could use the fact that the two acute angles in a right triangle are always complementary. So angle B is the difference between angle A and 90 degrees, and substituting the value we just found for angle A, we get B is approximately 38.9 degrees.